the heart of biggest open source models in the world. And we try to make it open source because we want to leverage from a strong community which can use it and progress in it. Now, why does all these things happened in the last year? Well, basically, there was a tendency, I would say, in the last 20 years related to what I call here the extreme scale era of machine learning, and where basically computing was at the heart, basically, of a big phenomenon in terms of being able to go into what we call brute force. It started with CPU-based computing with limited real powered impact, and I think some of you are familiar with Watson of Deep Blue. Then to things related to GPU-based computing, where you had basically the AlphaGo, if you are all familiar with that, of DeepMind, in basically playing that kind of game. And recently, in the last years, we've been in the era of supercomputers. And today, there's a bunch of supercomputers which are being built around the world to run these super large models. And basically, that was the big trend in making those large models computable. The fact that they can be computable is very important because you need a kind of architecture which scales and on which you can find what we call a way to train those models within a reasonable time. So you need to find a way to parallelize basically the calculus. And these supercomputers, which are now being built in the world, are basically at the heart of making this training possible. I think an effort has to be done in Africa. I think you'll have some discussions today about what are maybe the kind of key messages that we need to push basically within the AI realm in Africa. But I think one thing which is missing is, of course, a consortium willing basically to make computing available in Africa for the different stakeholders that can be located somewhere or can be distributed. These are questions that we can be asked. But that, I think, would be a very good initiative coming from this conference that we're doing at the moment. The second thing also which was very important is, of course, also a key date in the machine learning or NLP community, and that key date is 2017. A lot of these large language models are based on what we call natural language, again, just like large language, natural language processing. And natural language processing was there for many years and was based on what we call statistical rules. These statistical rules are mostly about basically taking words and putting them in bag of words and looking at how similar they are. And this is basically how you classify basically the words. So a man is similar to basically a king, a queen, a woman. And basically these kind of correlation based are at the heart of the techniques that have been being used in speech recognition and all these techniques. Now, one of the problems that we had in implementing NLP, and the reason why it didn't scale so much, is that the classical people who are building these NLP concepts were looking at architecture to build them, which is normal because you need a hardware architecture, which are what we call recurrent neural network, LSTM, GRU. These kind of architectures have some drawbacks. The first one basically is that attention has to be to the rescue. It means that we cannot learn long dependencies. We fail in basically long sentences. And if you had basically the opportunity to use these tools, which are like ChatGPT in general, you can construct very long text, long sentences with a given prompt. The second thing also, which turned out to be also quite a disadvantage of the techniques we've been using, is that the training is mostly sequential. So sequential means you can do it only after you did something. So of course it takes a lot of time to train. And so basically they're not parallelizable. And in general, you have to know in research, good ideas are ideas which can scale. If you have in your life a good idea and the idea cannot scale and is not parallelizable, then it's not a good idea because it means that you can cope with a situation of only 2, 3, 4 parameters. And then when the number of parameters or the number of constraints explodes, then you're totally stuck. And of course, your solution fails. And in general, you need basically that as more the problem becomes complicated, the more you can be able to find a way to parallelize your system to be able to cope with that situation. And so before 2017, we were stuck with that. And 2017, a very nice paper was published by the team of Google, Google Research. And basically it was called Attention is All You Need. And by the way, today, within the community of people doing machine learning, you have a lot of talks which start with attention. Attention is what you have to do. And what the message about that paper is important is that they came up exactly with the solution of solving the two problems I had mentioned before, solving the problem of learning long dependencies and the parallelization. And for doing that, they came up with an architecture which is called the transformer architecture. And in fact, in the GPT, the T means transformer. The G means generative and P means pre-trained. And in fact, that kind of architecture, by being implemented, enables to solve the questions we were asking. So when we talk about LLM, what do we mean and how does it work? Well, LLM stands for large language models, and it's a type of machine learning model that uses natural language as an input and output. And they're trained on a lot amount of text data. Now, of course, you have images, multimodality, we can talk about it, and can perform a variety of end tasks related to natural language processing. Compared to classical techniques where you optimize or you train your system to solve one use task or one use cases, these models are able to cope with a lot of different tasks at the same time, and they're also able to tackle unseen tasks. And these generalization capability is at the heart of what makes them extremely nice. So in general, what you have a text instruction, and the output is an answer. It could be a text, it could be an image, it could be a video, it could be a sound, whatever you want. They are generalists in the sense that they can tackle broad tasks just from instruction. Whereas classical deep neural network that we're using were very specific in terms of being trained to solve one specific task. And we human in general, when we're trained, and this is how the machines work in multiplication, we're trained in addition, we are still able by combination to know how to solve, for example, division. And these machines are the same thing. When you train them to be good in multiplication, to be good in addition, quite remarkably, without having them been trained to do basically division, they will find a way to solve that case that we're talking about. And of course, their capabilities increases as the size scales. And as of today, they're one of the main business and research interests in machine learning. So, what does basically modeling a large language model mean? Okay. Well, in fact, it's quite easy, and I'm going to go a bit deeper in maybe a bit just one slide of maths, but I mean, there's nothing mathematical about it. But in general, what you want to do is generate the next word, the next sentence, the next image. And for doing that, it's based on probabilities. You will implement a system which will learn a conditional probability distribution. What do we mean by conditional probability distribution? Well, what you want to know is if I give you the sentence, the capital of the United Arab Emirates is Abu, you would like to know what's the next word X. And so what you want to know is what is the probability that X is equal to Dhabi, knowing that the capital of the United Arab Emirates is Abu. What is the probability that X is equal to Paris, knowing that the capital of the United Arab Emirates is Abu? And of course, if you get all those probabilities of all the different, I would say, next generated word, you will take the most likely, and then that's exactly the decision or wording that you'll get as an answer. Now, to do that, you will need to learn that conditional probability. So how you do it, it's what we call function approximation. You will do a projection of that function in a basis based on all the data that you have and learn in that basis the weights corresponding to that. So for people in the public who did a bit of maths, one way to learn a function is basically to project it as a polynomial and to do what we call a polynomial approximation. Okay, so you'll say P of x here is equal to a0 plus a1x plus a2x squared plus a3x cubed. And you will do a kind of approximation with the degree of a polynomial, which is the size of your model. And the coefficient is basically the parameters of your model. Learning them is easy because you will not need to minimize some kind of metric. And with all the data, you will be able to find those coefficients. Now, doing that is not a good technique because we don't know how we can learn quite rapidly this property distribution with this huge amount of data based on the polynomial approximation. It's better to have a hardware architecture which can do that because you already exhibit the hardware that does it, and have also a technique which can learn in a scaling manner and in a self-supervised manner. And so we go back to that paper that I was talking about. That paper exactly proposed basically the kind of architecture which can learn that distribution. And that architecture, as I told you, has the properties that we were looking for, and it's the transformer. And second, it's within the realm of AI, is self-supervised problem. And this is very important because if you had to label all the data that was you're getting, it would be impossible to do it. Now, of course, I won't go into detail. In general, the notion of word does not make sense because depending on the language, what is a word in a language? Okay, is it because it's just the least representation? We have another way of defining words in the language of large language model. These are called tokens. Okay, and you have a process of representing basically the language with tokens, and this is called tokenization. For example, in Arabic, you have alif. Alif can be written in a different manner. So you don't have one letter for the same. And so depending on the language that you do, you need to do something. But this is something else that I'm not going to go in detail, but just to understand that when we're talking about language, is also transposing that kind of classical text that you have into a sort of a least representation or at least an alphabet which represents what we're talking about. So the kind of things that we worked and I worked on these things dates back to basically 2021. And when I joined basically the UAE in 2021, one of the first things that I wanted to kickstart was running the first large language model in Arabic. And large language models in Arabic are extremely interesting because Arabic, and it's the same for a lot of African languages, has big issues. The first is that it's not the same which is spoken in all the countries. So that makes already the amount of data set quite reduced. Second, basically, the kind of data that you have available on the web is quite limited. The majority of people in Arabic countries, unfortunately, now speak English, write in English, comment in Facebook in English, and even do not write in Arabic when they want to speak in Arabic. They write it with, I would say, classical letters or alphabets, and then you have the transition or the translation in Arabic. And second, also, a lot of the data that we have basically available on the web are mostly images. And learning with data set, which are images to do text, is extremely complicated because you need to go through a process called OCR, which we did not do, by the way. But said that, what I want to get as a message is that when you kickstart any kind of large language model in a difficult setting, that enables you to learn exactly how to exploit to the maximum you can the data set you have. And this experience was extremely useful for us to build after Falcon, where we understood that it's not just about the computing, which is important, but how you maximize basically the data set that you have in terms of usage that you can do. So we released, by the way, Noor in April 2022. We started basically publishing in the Etihad newspaper some articles which were Noor generated. Especially there was a COP27 at Sharm el-Sheikh last year where the topic was sustainability, and we were given some prompts in terms of sustainability, and we started kickstarting some articles related to that. When we did that, of course, the second question we asked ourselves is, we built a model. I didn't say it, by the way, it was a 10 billion parameter model. The fact that we stuck ourselves to 10 billion was mostly because the availability of data could not enable us to train a bigger model. And so just after that, we kickstarted some reflection on saying to ourselves, well, we don't want to do just Arabic. We want to incorporate codes. We want to incorporate different languages and build a model which could have all these capabilities at the same time that what was being released in the community at that time. When we looked at the numbers, those numbers were extremely, extremely high. Megatron was 530 billion parameters. You had basically Jurassic, you had basically Gopher, and all these numbers were extremely high. And so if we wanted to build a model, which we wanted to open source, which were within that realm, we had to build a model of more than 500 billion parameters to be within the top 5, basically, as one of our goals. Luckily, at the moment we were doing that, a nice paper that I strongly encourage you to read appeared. It's the paper of Kaplan, and that paper made a big disruption in our community. It proposed what we call some new scaling laws. And basically, what that paper was saying is that it's not necessarily only the size which matter, but there are three things when you build a large language model which matters. The first one is, of course, the number of parameters. So to give you an example, it's like if you have a kid, well, he needs to have a certain number of neurons in his head to be able to at least process information. So somebody who's 2 years, 3 years old will not have the same number. So the older he is, up to a certain age, of course, because you get old, you need a certain number of neurons in your brain. So the more neurons you have, the better it is. Second is the quality of your data size, the data set and the data size. So to give you the same example, if you want to train a kid, it will be the number of books that you put him at his disposal, and also the quality of the books on which he's going to learn. So you need to make a very good choice in book. If you want a kid who becomes in his future a student who is more math oriented, you will give a data set to your kid on doing more maths than literature. Now, if you want to shape a generation of students which are more literature oriented, language oriented, you will start giving them more books which are of the literature side. So what it means in the way you educate people, the choices of the books that you give them impacts basically their reasoning capability, more into math, logic, memory, history, or something else. And this is, by the way, something that we found when we trained this model. By doing the right choices of percentages of data set corresponding to more code or less, to more Wikipedia pages than less, to more textbooks which are more like literature or facts, you come up with a model which is more oriented towards or geared towards a certain, I would say, mindset. And the third thing which came up, which was very important, is that how long you train the model is extremely important. The number of epochs is extremely important. So the longer you train, the better it is. To come back to the example I gave you, if your kid reads rapidly a book, he's not going to be able to memorize everything. So the more he reads, the more he spends time. So he needs to do his revisions to succeed in an exam in 1 day or 6 months. This has a huge impact on how he can basically perform within the exam. And so by playing with these three, we saw that we could come up with a model with a low number of parameters, and we came up with basically a number of 180 billion. This is why Falcon today is 180 billion. And with that number, we saw that we would be able to come up within the top 5 basically large language models in the world. And what provide us more confidence is, of course, that exactly at the moment where we were launching our training, a model called Chinchilla appeared. And that model was a model with only basically 70 billion parameters and was outperforming all the others, which showcased that the approach that had been proposed in that paper was the right basically approach to be able to construct models. By the way, today, people are continuing to construct large language model within the size of 7 billion to 70 billion for information. And these models are now having great capabilities with the super large language model. And I think in the future, we'll be coming with models around 30 billion parameters and even 10 billion parameters with outstanding capabilities. Below, I'm not sure, but what we're seeing is a market where models with lower parameters are extremely performant. This is also, by the way, extremely good for us because you have to know that whenever you build a super large language model, I didn't mention that, you also need to serve it. And serving a model which has 180 billion parameters, you cannot run it on your laptop, you cannot run it on your phone. So, of course, the progress that we're seeing in making models of roughly 10 billion will provide basically a massive opportunity, I think, for everybody to have what we call large language model on device. And just to give you an idea on how this is important, as you all know, e-learning did not kick in Africa. And one of the reasons that e-learning did not kick in Africa is because, of course, the bandwidth connection that we have, the telecommunication infrastructure that we have is not so good. So starting basically, and I mean, many of you during COVID wanted to have e-learning connection. The kind of video costs you money. When you're able to bring LLM on the device, you don't need a connection anymore. You have all the knowledge of the world within a pocket in your phone. You can imagine how disruptive this can be for the whole educational realm in Africa, where people can download a model and basically have all the encyclopedia of the world in their phone by just asking questions. This just gives you how important it is for us to continue constructing models which are open source so everybody can use them, and making them smaller to a size which is basically being implementable within a phone. So just two slides to tell you that, of course, on our work that we did, we released a first one, which is a 40 billion parameters. We released one, which was a 180 billion parameters. If you want more details on these models, they're open source. You can download them, and that's a good opportunity. Now, of course, I gave you a couple of examples related to education, and I have like 3 slides before I finish. These LLMs, of course, go beyond a lot of applications. And I think some of the colleagues were speaking about them. They go from what I call content creation, with things like image generation, video generation, voice generation, game design, to things like content creation and analysis with text summary, video summary, visual analytics, to things like task automation. And today, also, what's interesting is that we're seeing a couple of stakeholders. I should add Falcon here, by the way, which are providing what we call the operating systems of the Internet of Intelligence. My own gut is that there's going to be consolidation of the market where we're going to see only maybe 5 or 10 OSs which are going to be there, and a bunch of startups which are plugging their APIs and serving basically their customers through that. Now, something that is extremely important for you to understand is that building these models, there are some key considerations. I'll go roughly around them, but I think they're interesting for you. They go from the data that you need to consider, to the model architecture, to the pre-processing, to the fine-tuning, to the evaluation, to the deployment, to the explainability, to all the issues that we're seeing today on privacy and security about how you deploy this on premise, and also to the bias and toxicity that you need to take into account. So building an LLM, when you decide to start going in that journey, are a lot of processes that you need to take into account today. I'll finish to tell you that the challenge of doing that is at the heart of what we want to push today in Africa. It goes within 3 realms that I think are solvable. One is, of course, the computer resources, on which I think we need maybe all to share our own experiences, initiatives, and maybe come up with a common platform for that. The engineering complexity, where I think there's a lot of talent in Africa. To be honest, within the realm that I built, there were a lot of Africans which were at the heart of the Falcon, and you can see it also in other models on which a lot of diaspora basically has been at the heart of building this. And the last one, which is also at the heart of our own basically protection of our know-how and also basically culture, is the data sourcing. I finished now, and I hope it was interesting for you.
Thank you very much, Professor Marwan Dada. This was a great presentation on challenges building LLMs. For the sake of time, we are not going to take questions because we are really late for questions. We are just going to go to the next speaker, Mouloud Harif. No, right? Okay, let's go. Thank you again, Marwan.
Thank you all. Thank you. It was great.
Presentation. Yeah. Okay. So Sofiane.
Sofiane? We need Sofiane for his computer and the presentation here.
Just go. We do. I don't have another presentation.
Les présentations.
I'm on the
Chauffe.
I'm going to use the drive.
It's on the drive.
Second. شو نروح نقرأ نورة.
على بالك انا بشوف j'utilise le micro, ça va faire peur.
You're going to share the presentation?
Il est fermé. Hein?
You can take the presentation. And Peter. Share. Move.
Assalamu alaikum. Shukran. At the end of the day, it's been a long day. It's been a very rich conference, and presenting after my friend Professor Marwan Deba is a privilege. I don't know if you realize the privilege that you have. I mean, unfortunately, he couldn't be with us, but he insisted on presenting remotely. So I'm going to talk about a different topic. I'm going to continue the conversation that Lavina, my friend Lavina, started earlier today on AI and ethics and governance, and that my dear friend also, Dr. Lamin Sarr, will continue after me. So I'm not an AI scientist. I'm not a data scientist, like Heikel said. Even though I have a technical background, so I'm an engineer. I even worked on AI as part of my master degree, and it was at a time where most of you were not born. I don't know if Morad was born at that time.
I wasn't born for sure.
You were not born.
I wasn't.
And it was a time, listen, Morad, you heard about the concept of AI winter? It was just before the AI winter. Yeah, like, I mean, the other one, I wouldn't be here, okay? Not the first one, the second AI winter. So I worked on neural networks, but obviously I even designed a software based on neural networks to help detect. I was working at the research department of Renault, the French car company, and the software was to detect spark failures. You know, the car spark failure. So obviously we didn't have the algorithms that we have today and the computing power that we had, and that explains why shortly after that the the second AI winter started. So let's talk about policy and governance. A little bit about myself. So again, summarizing 30 plus years of work experience is not that easy. So I've done different things in my life. These are a few of the organizations that I was connected with. The past few years, I've been working mostly on digital policy, digital strategy. I am connected with the Center for AI and Digital Policy. It's a policy and research think tank based in Washington, D.C. And I'm also a consultant, an advisor, and a lecturer. What is this? Yes. And recently I joined the IGF, the United Nations Internet Governance Forum Policy Network, with researchers and practitioners from around the world, working on AI policy. And this year the focus was on the global south, so including Africa, obviously. Why is it taking so long? It's a PowerPoint. Huh? But is it any easier just to download the PowerPoint? Yeah. Because I sent in a PowerPoint, shouldn't that take that long? Yeah. Also, yeah.